Hello everyone, welcome to section 2.4. There's a big difference between the first three sections and the sections that we're going to start from 2.4. In 2.1, 2.2, 2.3, even if we introduce the definitions of left side limits, right side limits, two side limits, and limits to the infinite, everything that we did, all the examples that we looked at were on functions defined visually. Now we're going to look at computing the same things, but from function defined algebraically. And then the question is a lot more challenging. So we're going to first look at a way to compute limits, which is basically a guessing method, or of course, we're not going to say like the guessing method. It's not very nice. So formally, we're calling this the numerical method. Okay, so the numerical method is one way to guess limits of functions defined algebraically. So the big goal here is we want to compute limits for functions defined algebraically. So the first approach will be guessing limits using numerical approach, i.e. by looking at the numerical behavior of the output. So basically, like in a nutshell, the big philosophy is just plug in values and just look at the outputs and try to see a pattern. If you see a pattern, it's getting closer to a number, then the limit exists. You're getting numbers are getting bigger and bigger with no upper bound. It goes to infinity, etc. Okay, so it's really studying tables of value. So the definition here of the numerical method, so in order to guess the value of a limit numerically, so we have, at the end of the day, 4 types of limits. 5 if you count the two-sided limit, but of course if you have to guess a two-sided limit, what you do is you guess the left, you guess the right, and then you compare. So there's really nothing to do to some extent. So how do you guess left-handed limit at x equal a? So what you have to do is construct a table of the function with inputs from the left. So these inputs, they need to be strictly less than a, and typically if you want inputs that are less than a, what you can do is just use a and subtract small values. So me typically, and you'll see this in my tables, I'll be using a minus 0.1 and then a minus 0.001 and a minus 0.0001. And of course you can continue. So by subtracting these small numbers from the input the number a, of course, you're going to get inputs that are strictly less than a. So for right-handed limit, so you're going to use the exact same idea, but you're going to construct a table of outputs with inputs that are from the right, so strictly bigger. And typically what I'll be using is that, well, if we care about a, just by adding 0.1, and then if you add 0.01, so of course when you're adding a smaller number, you're getting closer, 0.001, and typically this is enough to find a pattern. And of course by adding from a to a 0.1, 0.01, 0.01, you're getting a bunch of inputs that are getting closer and closer to a, but are on the right side, so they're strictly bigger. For limits going to infinity, so you just construct a table of outputs with inputs getting larger and larger. Typically what I'll be using for inputs, as assuming that they are in the domain, of course, I'll be using 10, 100, 1,000. I mean, if you're really in the mood, you can use more, but typically I will be using just 3. So these values will go to, of course, are getting bigger and bigger. So this will allow me to study the numerical behavior of your function for large positive inputs going to minus infinity. So you construct a table of outputs with inputs that are getting arbitrarily large, negatively speaking. Sorry about that. So typically I'll be using minus 10, minus 100. Of course, I'm assuming here these are in domain. They will be typically. And I will typically use only 3, but sometimes you need a bunch of them to really feel the pattern. Okay, so you're basically just computing outputs, and you just need to learn how to choose the correct inputs if you're studying a left limit, how to choose inputs if you're studying the right limit, or if you're going to infinity, just feed it. Numbers are getting larger, or minus infinity larger, but negatively speaking. So like big remark here about the tables, what we're expecting you to do, because normally you have to build your own table. We're expecting you, when you're constructing a table, so the first point, your table of outputs should have at least 3 inputs. So if you're making a guess, you should do a guess using at least 3 value. And you'll see, of course, since I'm saying at least 3 because I'm a lazy piece of shit, I'm going just to use 3. If you use more, it's good. But 3, I want 3, minimally speaking. The second thing here, this is a remark about one-side limit. So if you are studying limits on the left or on the right, you want to be close. So you want to choose values that are close, but not too close. This kind of seems a bit counterintuitive, but the idea here is that suppose you want to know what's going on around 1, let's say on the left, you can start by using 0.9, 0.99, 0.99. Of course, there's always this special person. I'm going to use 0.999999999. Yes, of course, if you use 0.9999999, the idea here is that suppose you're using 10 nines after your 0, you better replace every single x value with the exact same 0.99999. If there's a 9 missing or a 9 extra, it's going to completely, in general, screw your computations. Okay, so you want to be close, but remember you have to compute outputs. If your input is complicated, then the output will be complicated to compute. So same kind of remark for limits going to infinity or minus infinity. You want to use big inputs or big inputs negatively, but not too big. You know, you don't want to use a quadrillion, okay, as an input. It's going to be very difficult for you to evaluate your function for very large inputs, positive or negative. All right, let's go look at an example right away. All right, first example. Well, it's actually the only example in that section, but we'll have a lot more examples in the next section too. So we have the function f of x, which is sine of x over x. We want to use the numerical method to guess the limits around 0 to infinity and to minus infinity. Of course, if we say around 0 here, okay, so this means that we want to check the left limit and the right limit. Okay, so when we say around, it's implied that we want the left and the right. So I've already have like little rectangles for my table. Normally you draw your own rectangle, as you can see for every single rectangle. I have a column for the x's or the a's, and I have a column for the y's, and I'm going to compute using my calculator. So let's do the left and the right of 0 first. So as you can see here, my first table will be to guess the left limit around 0. The second table here will be to guess the right limit around 0. The third table will be to guess the limit going to minus infinity, and the last table will be to guess the limit going to infinity. So the first thing you need to be comfortable with here is creating these tables, so the x column and the y column. So if we are around 0 and we're doing the left first, so here the first one, that's my table going to 0 minus, so we need to choose inputs that are close to 0 but smaller. So if I take 0 minus 0.1, minus 0.1 will be very good. Let me just change color here. Okay, so minus 0.1. So we want inputs that are getting closer. So minus 0.1, minus 0.01, and those are my favorite ones, minus 0.001. So 3 inputs. As you can see here, these inputs are getting smaller, are getting closer to 0, and they're all smaller. So these are getting closer to 0, and they're all on the left side. They're all like strictly less than 0. And now what you do is you compute outputs. So here we have a function. In these questions, the function are provided. So you just replace every single x by minus 0.1. So if you compute, make sure your calculator is in radian if you have trig functions to deal with. So if you compute sine of minus of 0.1 divided by 0.1, you can verify that it's going to give you 0.998. So 0.998, etc. You don't need to put all the digits here, just the most significant ones. So the next one, if you replace x by minus 0.01, you're going to get 0.99998, etc. And then if you replace x by minus 0.001, again, make sure you do this on your own, using your calculator. Make sure you understand how to compute the outputs here, but I'm just doing a bunch of evaluation inside of f. You're going to get 6 9s and an 8 and etc. Now, 0.998, 0.9998, 0.999998, I can see that these numbers, they're very close to 1, and they're getting closer and closer to 1. So the best guess here is to say that the limit as x approaches 0 minus of f of x is 1. So that's our guess. Okay, so that's our guess for the left limit. Now, if you do the same thing on the right, again here, it's important to understand how to construct inputs slightly bigger than 0, but getting closer. So my favorite ones here, 0.1, 0.01, and 0.001. And actually here by symmetry, I'll just do it because the evaluations are a bit redundant. But if you evaluate, poof, you're going to get, it's just a coincidence here, but you're going to get exactly the same thing. Okay, so of course this means that the guess is exactly the same. We're getting 1 again. Okay, so left and right limit, the guess is 1. And this means, of course, that the two-side limit, I'll write that as a remark in a second, but the two-side limit, because both sides are the same, is equal to 1 also. Now let's go to minus infinity. So my favorite numbers going to minus infinity, I always use the same. So minus 10, minus 100, minus 1,000. I always use these three. If I need more, I use more, but normally they will do the job. Okay, so here, if you replace x by minus 10, sine of minus 10 divided by minus 10, you can double check that this is going to give you minus, minus 0.05, and then 5, okay. Sorry, I had to blow in my mic. And then at minus 100, sine of minus 100 divided by minus 100 will be minus 0.005. And at minus 1,000, you're going to get 0.0008. Of course, these numbers, they go on, okay, forever. I'm just writing like the significant digit. So here I can see my numbers. Even if they change sign, they oscillate and they get closer to 0. If I have to guess here, my limit is going to be 0 for the limit going to minus infinity. So that's my guess here. And then going to plus infinity. So I'm using my classic numbers, big numbers, number getting bigger. So 10, 100, 1,000. Normally this is all that you need. And now, actually, this one again by symmetry. Okay, you can try it, but boom. Okay, so the outputs are exactly the same. This is just a coincidence here. It's not always the same. So same guess. So we have that our limit going to infinity is 0 also. So I have my 4 limits. My left limit. My left-handed limit for 1, my guess was 1. My right-handed limit for 1 was 1. Also, for 0 was 1. And going to minus infinity or plus infinity, I got 0. Couple of remarks since we're here. Couple of remarks. The first thing I want to remark here is actually the domain of f. Okay, so if we think about the domain of f, okay, so the domain of f, I'll write those remarks in red. It's not the point of that question, but might as well talk about it. The domain of f, there's only a denominator here. X is going to be 0 when x is equal to 0. So the domain is everything but 0. Okay, so everything but 0. So this means the interval from minus infinity to 0 open, union 0 to infinity. And here you can see that when you look at the domain and you look at the open endpoints, they correspond to the four limits that we just guessed. So for example, the left side of 0 is here, the right side of 0 is here, minus infinity is here, and infinity is here. So the first table was for x going to 0 minus, the second table was for x going to 0 plus, the third one was for x going to infinity, and the fourth one was for x going to minus infinity. And actually, normally in a true question, and this is what we'll see in the next section, we don't really tell you which limit to compute. We say, here's a question, talk to me. Give me some information about that question. The first thing you do is you compute the domain. We know it's defined everywhere but 0. But how does it crash? How does it behave around 0? Well, the limit will tell you. Normally, you're used to, if it crashes at 0, there's a vertical asymptote. There's no vertical asymptote here. If I had to comment about what's going on around 0, well, the left limit and the right limit is 1. So if we had to have a visual conclusion, well, here we actually have a hole at 0, 1. So around 0, the function does not blow up to infinity. It's very close to 1. How are you going to illustrate that? With a white dot at 0, 1. Meanwhile, when you say a function goes to infinity and minus infinity, does it go up forever? Does it go down forever? Or does it get closer to an horizontal asymptote? And of course here, we see that this function at minus infinity or at plus infinity, they have horizontal asymptote on both sides at y equals 0. So those limits, they give you precious information about the function. We don't have the graph in front of us, in our face, but these guesses, they give us information, and we can piece out that information together and then reconstruct the graph of the function. And this is the whole point of computing limits. So we have a domain, and then these four endpoints, they induce four important limits to compute. And of course, right now we just know how to guess it. So we build these tables to guess the limits, but then with these guesses, we're going to get some information that we'll be able to illustrate later on. Anyways, enough talking for this section. That's it. Bye-bye.